My name is Kevin, and I'm from Team 21229 Quality Control, and we were the 2023 World Championship winner last year, so we would like to share with you some tips about building a more reliable robot. So last year, we built three robots for the Power Play season. Our first robot, which is right here, had a very customized design, and we designed a lot of plates on it and used a CNC cutter to manufacture a lot of those plates. But we had a lot of maintenance difficulties on our robot, and it actually wasn't very reliable. So we took the learnings from our first robot and built a second bot, which we kept in mind to make more reliable, and that helped us win the Colorado State Championship and also get the world record in season qualifications up to Worlds. And finally, for our third robot, we built it specifically for the World Championships. We made it more reliable and also faster, which helped us win the World Championship and also the Innovate Award winner. So I'll be using this firsthand experience from last year to be giving some tips about building a reliable robot. So as a show of hands, who is not familiar with last year's Power Play game? Okay, so since like very few people raise their hands, I'm just going to give a quick overview. So this game is not as complicated as this year's game. So um this that is a cone and you score it on these junctions which are like yellow sticks. So basically score these irregularly shaped cones on these yellow sticks called junctions, and that's basically it. So as a general outline in my workshop, I'll be splitting this into two parts. First of all is designing a reliable robot, and second is maintaining a reliable robot. So for designing a reliable robot, I'll be talking about how to keep your robot simple and straightforward, also known as KISS. I'll be talking about having a modularized design, designing reliable mechanisms, preparing for possible failure in tournaments, maximizing error margin, and also optimizing 3D print strength. For the second part, maintaining a reliable robot, I'll be talking about Loctite and screws, checking heavily moving parts, and also cables and cable connections. And at the end, I'll be taking any questions you have, and I'll try my best to answer them. Now moving on my first tip, which is keeping it simple and straightforward. Our first robot, which wasn't very reliable, was the opposite of that, and it was customized and complicated. So we wanted it to be perfect, so we had a highly customized design and catted almost every plate and every hole in it. So this is a plate on a robot, and it had a ton of holes on it to mount a bunch of different stuff, and it was really complicated. And we used a CNC cutter to cut most of the plates, and if one of the holes was off by a millimeter, we would have to redesign the whole thing. So it was very difficult to improve upon. And we also had some other reliability issues, which is our heavy virtual 4-bar intake had counterweight springs that broke really easily. We had very long horizontal slides, which are 6 feet long, that were placed in the middle of our robot, which meant that control hubs and expansion hubs couldn't be placed there, and they had to be placed on the side walls. So they were mounted right there. And the vertical slides on our robot had some lag between each other, and our outtake mechanism was just not reliable at high speeds. So because of this, for our first tournament, our first spot ranked number 10 out of 15 robots. So we decided we needed a fresh start on our second robot, and we made sure to have it more simpler and modularized. We used a Go Build a drivetrain this time, so we could easily build a drivetrain in like a day. And instead of putting really long slides in the middle of our robot, we put them on the sides of our robot. And we drove it with a linkage that was powered by a servo. And because of this, the hubs could be placed under the drivetrain and not on the sidewalls. So in later I'll explain why that was helpful for reliability. We have an outtake, which is here, and it is 3D printed and shaped like a cone and gives a lot more contact with this scoring element. So that made the outtake more reliable and stable. And because we didn't put any servos on that outtake mechanisms, we didn't have any need to wire cables on it on our outtake slide, which also made it more reliable and less points of failure. Finally, because of all of this, we were able to score the world record in season qualifications. So as I talked about, it's just important to keep it simple and straightforward, so it's easier to build, it's easier to design, and it's less likely to go wrong in a competition. Next, on to our next tip, I'll be talking about having a modularized design on our robot. So we designed our second robot into 3 easily detachable parts, which is our intake, outtake, and drivetrain. You can see here, this is our intake, and this is our drivetrain, and this is our outtake. So our outtake could get mounted on this part, our intake got mounted in the front of a robot. So the benefits of this is that it's really high efficiency because you can build different components at the same time and have multiple members, all of your team included, doing that. And it's also much easier to maintain because the intake and outtake can be removed by just loosening a couple of screws, which means that it doesn't take a long time to replace a part that broke. Now I'll be moving on to my next tip, which is designing reliable mechanisms for high speeds. This is our very first outtake mechanism. It worked at slower speeds, but at high speeds, it got a bit less reliable. So it provided almost no support to the cone, and when it was going at really high speeds, the cone would easily fall backwards, and it was not reliable. So for our second robot, we made our outtake 3D printed and shaped like a cone, and that made more contact with the game element and therefore was more reliable. We also made sure to have a junction guide. You can see here, and it's shaped like a semicircle and can easily force the junction under the cone for more error margin when scoring. And we also added some tape inside of that guide to maintain friction and also force the junction to the center and maintain it there. This is another example of a reliable mechanism, which is our World Championship bot's outtake. And we were ambitious with this subsystem. We want it to be very fast and still be more reliable as it travels at high speeds. So the main part of this is our outtake ring. So it's like a circle and a rectangle put together, and I call it the outtake ring. It's 3D printed and it acts like a frame to put the cone in. And we have a servo-driven latch, which is right here, that can rotate to control whether the cone is secured in the outtake or whether or not it's ready to be released. So that just completely makes the outtake reliable when it's traveling super fast. Our outtake ring has an interior angle. You can probably see this slant right here. This shows that it has an interior angle and it best fits the cone for more reliability. Finally, we have this extra chip right here, and it provides extra support to the cone without making the entire outtake ring heavier. So now more about the chip I just talked about. Originally, we did not include this chip, and the cone can droop down, as you can see right there, because that side of the cone did not have any support from the latch, so it could droop down slightly and make scoring much harder. So after we added this chip, you can see that it kind of blocks the cone from falling down, and it doesn't droop as much, which makes scoring easier and also more reliable. Another example of a reliable mechanism is that our intake was extremely heavy because we needed to do a lot of stuff on it and a lot of parts. So our servos couldn't lift the intake up without risking it overheating. And one solution would be counterweight springing, but normal springs wouldn't work because it exerts different forces when the intake is extended at different heights. So our solution was that we used a constant force spring, which looks like this, and it actually exerts the same constant force at different heights of the intake. You can see we used it right here. I know it's kind of hard to see, but it's kind of like a circular part that's extending out a bit. So the benefits is that the lift becomes weightless. The servos can lift it much faster and reduces its time by half, and it prevents the servo overheating, which makes it more reliable. So this is a video showing us testing our spring. So there were no servos involved in this. It was entirely done by that spring, and it becomes weightless and anti-gravity. Another thing was that in autonomous, it was very hard to put the robot at the exact same spot every time, and that could lead to our autonomous being inaccurate. So we installed something like an aligner for us, which is basically a beam that can rotate in and out. So you can see right here, the aligner is folded in because we don't want it, in actually running the robot, we don't want it to get caught on something. But just before we run our autonomous, we fold it out, you can see here, and align it to the middle of the tile. And the middle of the tile has some special mark on it, which we just align there. And then, so this picture shows our robot just being aligned and us doing that. So it makes our robot placement more accurate and more reliable. Another thing is that if our robot needs to move a lot in autonomous, that could mean that it could gradually lose track of its position and therefore be less reliable. So instead, we built a turret, which is a bit lighter than our robot, and it can aim to score on either side of the junction. So that makes it faster and also more reliable. And now moving on to my next tip, which is preparing for a possible failure. And I'll explain why it's so important because even if something is unlikely to happen at a real match, it could still actually happen, and that could cause your robot to not be able to do anything in a match or to completely die at a tournament, which means that the hard time you spent building, designing, and programming your robot just went to waste because it broke and couldn't do anything at the competition. So it's always important to anticipate failures and be able to fix them. So last season, one failure was that robots could only control one cone at a time, which meant that if a cone got stuck in our robot, then our robot couldn't do anything without getting a bunch of penalties. So this is our first robot. As you can see, we had to create walls to mount the control hubs on, so it was very boxy and the cone could easily get stuck. So in our second robot, we made sure that our hubs were hidden in our drivetrain, which meant that we didn't need to create any sidewalls for our robot. That made it easier for the cone to slide out. And you can see it's pretty open right there. We also have a 3D printed roof, which is like a slanted pyramid, and it forces the cone out because of its slant. Another possible failure is whenever we fail to score a cone in autonomous, our outtake mechanism would still have the cone in when it retracts in. So when the robot reaches to grab another cone, we would get penalties, and that isn't desired. So Here's a video showing this happening. We're over here. Um, we failed to score, opponent dropped a cone in, and then we scored all 3 cones at once, which meant we got a bunch of penalties in that match. So I'll play it again for you to see it. This is when it happens. And then we grab another cone, possessing a bunch of cones at once. So that created a lot of penalties. Our solution to this is that we have an ultrasonic sensor, which you can see here, and it can detect whether the cone is still in our outtake. And if that's the case, our robot won't grab a new cone and we won't have as much penalties. Another possible failure is that when you use string to drive slides, if the slides get stuck or snagged on something, the string can easily become loose and get out of the spool, which will basically mess up your slides. And that can be really stressful to fix in a real competition. So instead of that, we designed a 3D printed string protector. You can see it looks like this. We included it at the bottom of the slides where the spool is, and it mounts to the bottom of it and encases the entire spool. So it prevents the string from going out and makes it more reliable. Another failure is that a robot can really easily get hit during autonomous and move to the wrong location. So instead of that, we use a PID to aggressively push back to its original position. And another failure is that when you use vision to detect something in auto, it could really easily go wrong. When we were last year, we had signal sleeves, and we detected them to determine what the robot would do at the end of autonomous. But color-based detection, like detecting colors, doesn't work as well during harsh light conditions because you may be practicing in your garage and it's kind of dim, and then you go to a competition and it's really bright, and then the color is shown differently in the camera and your auto gets messed up. So instead, we would recommend using April tags like this, and they resemble QR codes, are black and white, and it works in a variety of light conditions. Now I'll move on to my next tip, which is maximizing error margin. So it's important to have your subsystems be able to handle a bit of error because in real life, nothing will ever work perfectly the exact same time. So instead of trying to spend too much time perfecting that, you can pretty easily design your subsystems to be able to handle that bit of error. So an example of this is on our claw. So our original claw was designed to grab the middle of the cone. So the circle it encloses only has a 2.4-inch diameter, and it's hard for it to grab the bottom base of the cone. Our new improved claws are wider. You can see here it encloses a circle that's bigger. It has a 3-inch diameter because it's designed to grab the bottom of the cone. But you may ask then it couldn't grab the middle of the cone because it's too large. Well, we fixed that by having the claws be able to overlap to grab the cone at different heights and give it more error margin. So here's some pictures so you can see that more clearly. The original claw works when grabbing the middle or top part of the cone because it's just designed to be smaller and yeah. But however, it can only touch the cone at the bottom at the claw. So you can see here that there's actually a little bit of gap between the claw and the cone. It's hard to see, but there is a gap. And that means that only the bottom of the claw touches the cone, and it isn't stable. The cone isn't stable enough in the claw to be as reliable as we want it. So with our new claws, it's designed to grab the bottom of the cone. You can see here it fits pretty well. However, it can still overlap, as you can see here, to grab the top of the cone. And you can see the light blue claw is over the dark blue. And we made it so it can overlap by cutting off a little bit of the claw at the end so it can come together. Another type of bias is that the claw tip could be behind the far side of the cone, and the cone might not fully be enclosed in the claws when it's trying to grab it. So, um, so for our original claw, it had a very thick and round tip, so the cone could easily get repelled when it was being grabbed on. So here's a video okay, not that. Here's a video showing this. So we tried to grab it, but because the tip is round, it doesn't work well. Instead, for new claws, we made it have a smooth, sharp tip to force the cone to the center of the claws even when it's grabbed near the center line. And the center of the claws have some rubber bands for better grip. So not this one, but this one. So another type of error when we're grabbing the cone is that the claw could be grabbing it to the right or the left of the cone. And since we made our our claws wider, it could also grab the cone at a wider variety of places. And also with our sharp and smooth tip, we can pretty easily force the cone to the center and grab it. So this is an important example because the robot location might be wrong, but might be off by a little bit, but we can still grab the claw. We can still grab the cone. This is another example of maximizing error margin on our World Championship odds outtake. So I didn't mention this before, but it has a rectangle opening in the back of it to allow the cone to be dropped in at different positions and heights. So you can see here that this cone is being dropped in at a kind of horizontal angle, and the cone is being dropped in at a kind of vertical angle. And this rectangle is a little bit smaller than the diameter of the circle, which means that the top of the cone can still get in, but the cone is still going to be secured in the circular part of the ring. And this was really important for our third robot because the intake was traveling at really high speeds to make it score faster, and it might drop the cone at different positions. So without this simple rectangle at the back of our circular part of the ring, our robot would be really inconsistent. So this is a video of us testing our outtake ring and testing whether it has enough error margin. And here's another example of error margin and a reliable design. So once upon a time, our club broke and we still tried it out. So you can see here that this part of the claw is kind of weird, and it's because it broke. But we were still pretty surprised that it could still grab the cone and still transfer it and score. So that was really cool, and that would be a dream design of a subsystem where it could still work even if part of it is broken. Now moving on to my last tip about designing a reliable robot, which is optimizing 3D print strength. So actually a 3D print isn't really solid. It's most of the times kind of hollow. So you can see that this shows a chart of the infill, and the higher the infill, the more the 3D print is filled up. And the other way to increase the 3D print strength is to increase perimeter layers. And the perimeter layers is kind of how thick the outer shell of the 3D print is. So increasing that would just make the 3D print stronger. You can see that around at 40% to 70%, the 3D print looks already pretty filled up. So once you get to that point, maybe start thinking about increasing perimeters to make your 3D print stronger. One example of custom 3D printing we used is on our outtake ring. So a problem is that our 3D print was breaking at the area shown here because there was a lot of force exerted on it. But actually the rest of the outtake ring was not likely to break. So we use something called modifiers in process slice to print that area at 90% infill and print the rest at 30-40%. So that was significant because it increases the reliability without actually making it heavy, without making it a lot heavier. And this was really important because our outtake ring needed to be light in order to be fast and also to not overheat the servo that's rotating it. So this helped us solve these issues. And we also increased the perimeters on it to generally make it stronger. Now I'm going to be talking about maintaining a reliable robot. And it's important to maintain a reliable robot because you may think that after designing a really good robot, you can just do some driver practice for the last 4 weeks and not have to do significant changes. But that's actually not true because screws can get really loose after running the robot for a long time. And we would recommend always using Loctite on these screws, so with threaded holes, so that prevents them from falling off. And I would recommend using button head screws on a real competition because they're more slim and they're also round, which decreases its chance of getting caught on something and snagged on it. Even if you apply Loctite to some screws, it can still become loose on heavily moving parts. For example, our turret carried our whole outtake mechanism and the slides, so it was really heavy, and it also had to rotate every match. And we found out that our auto was getting more and more inconsistent by the end of the season. And we finally noticed that it was because the screw attaching the motor was loose, which allowed the entire motor to rotate without motor shaft control. So this is a video showing that. I know it's hard to see, but if you focus on the Go Builder wrapper, you can see it's moving and twitching slightly. And that was because when we moved our turret, the entire motor could move along with it and not realize it. So that made our auto more and more inconsistent the more times we ran it. And here's another example of how things can get loose on your robot and why you should check them. Another thing is that our World Championship robot actually started out not being able to drive straight. So we took off all of the motors, and because it was moving a lot every time we ran it, so it could get damaged. So we took off all of the motors and used a program to print out how far the motor was spinning, and we realized that one of the motors was spinning faster than the others, always spinning more than the other three. So we took out that motor and replaced it. But our robot still couldn't drive straight, and we noticed this time we knew it probably wasn't a motor problem, it was probably something else on the hardware. So we put our robot on an elevated surface, so when we ran it, the wheels wouldn't make the robot go anywhere. And we realized that one of the wheels was making some weird sound on it, and we flipped over the robot and tried adjusting the bevel gears that were powering that wheel. And what was really surprising was that even though the bevel gears could only move like a millimeter or like a millimeter, adjusting it slightly could still fix that issue. So we adjusted the bevel gear very slightly, and that actually made the robot drive straight. So just a small difference could impact whether your robot can even drive straight. Moving on to my next tip, which is checking cable connection regularly. One time we were running our robot and our battery started making our robot disconnect, but not all the time, just sometimes. We took the battery out and realized that its cable was constantly bent and therefore it broke. So you can see in this image here, um, we looked at this cable, found out this, and like the outer rubber band shell, like the outer rubber shell of the cable broke and exposed the inside of the cable. So that caused it to sometimes disconnect and sometimes work. So make sure to check your cable connections regularly and replace any bad electronics. Another example of this is a hard lesson we learned, that our autonomous one time just completely failed, and we realized it was because one of our odometry cables was not plugged in completely. So make sure to check your cable connections regularly every match. We're getting started here with 3 of our 4 robots moving an autonomous here in semifinal. So that was kind of unfortunate, but you need to be prepared for this. So in summary, I first talked about designing a reliable robot. So keep it simple and straightforward. Don't make parts more complicated than they need. After you build your robot or design your robot in CAD, I would encourage you to take a look at every joint and every mechanism and see and like think about it. Is it really that important for me to use on the robot? Or is it going to be more building and maintaining pain? And next I talked about having a modularized design. So make sure that subsystems on your robot can be easily taken off separately, and that will just make it easier to build, easier to maintain, and easier to make more reliable. Then I talked about a few examples of designing reliable mechanisms, and then I talked about preparing for possible failure. So I know it could be like annoying because you think it's not going to happen in real competition, but just think about it. If it does happen, then you're probably not going to do that well in a competition. So identify everything that could go wrong and make sure to have something like a backup mechanism or a possible solution to fix it. Then I talked about maximizing error margin. So instead of trying to say, maybe next time move your robot 0.5 millimeters to the right when placing it, and then that will make it better, try to instead design subsystems to be able to handle that small error, and that will just be easier to make it more reliable. And finally, I talked about optimizing 3D print strength. So a combination of increasing infills and also increasing perimeters will generally make your 3D prints lighter but also equally as sturdy. Then I talked about maintaining a reliable robot. So make sure to apply Loctite on screws or you'll have a bunch of pain at competitions. And regularly check heavily moving parts often or regularly, because even when Loctite is applied, you still need to worry about those screws. And they can easily become loose on heavily moving parts, and they can gradually make your auto more and more inconsistent, as we found out last season. So regularly check that there's tight. And finally, regularly check cables and cable connection, as they can also become loose over time. So thank you for listening to my workshop, and feel free to contact us at our Gmail, YouTube, or Instagram if you have any questions, and good luck on the new season. Oh, yeah. Yeah.
I know it folds out, but how do you make sure it goes back in so that it just like
Um, yeah, we just fold it back in. Like, what?
It's like a piece of tape.
Yeah. No, when you're putting your robot, you can like touch it, I think. Like, yeah.